Alright, so today I'm going to prove a couple of different things to you guys. And then we're going to talk about what I have done. So the first thing I'm going to prove to you is that 0.999 repeating is equal to 1. This seems to violate the intuition of most people. These two things clearly look differently, so how is it that they can be the same thing? Let's call x this number. And let's see how we can manipulate this to get a slightly different value of x. So I'm going to multiply both sides by 10. And if I multiply a real number, which this is, by 10, it's the equivalent of moving the decimal place over by 1. So 10x is 9.999 repeating. But this number can be rewritten as 9 plus 0.999 repeating, which is 9 plus the number we started with, x. What happens if I subtract x from both sides? Well, I get 10 minus 1, 9x equals 9, which tells me that x equals 1. And because I haven't introduced anything to it, then this must indicate that x is 1. The next thing I'm going to prove to you is that 2 is equal to 1. Let's start by picking some numbers a and b with the property that a is equal to b. I haven't said anything about this. I'm defining these numbers to be equal. I'm going to multiply both sides of this equation by a. And so on the left-hand side, we get a squared. On the right-hand side, we get ab. Okay, no problem. Next step is I'm going to add a squared to both sides. So times a. So a squared plus a squared is 2a squared. And the right-hand side becomes a squared plus ab. Then, my next step that I'm going to take is I'm going to subtract 2ab from both sides. So, we get 2a squared minus 2ab is equal to a squared plus ab minus 2ab. And this right-hand side can be simplified to be a squared minus ab. So now let's look at the left-hand side. The left-hand side, I have a common factor of 2, so let me factor that out. We get 2a squared minus ab is equal to, well, a squared minus ab from over here. So now, both sides have a factor of a squared minus ab. Let me cancel that. And so we end up with the result I set out to prove, that 2 is equal to 1. And we got that by dividing by this thing. Okay. Let me just show you a second way of proving that. So let's call this method 1. Now, method 2, let me go down here a little ways and get some more room. Okay. So, method 2 of proving that. I'm going to start by proving an intermediate result, that 1 is equal to -1. So, it's fairly well known that the square root of 1 is 1. Okay, no problem with that. But we also know that -1 times -1 is equal to 1. Negative times a negative is a positive, and 1 times 1 is 1. So, I'm just going to take this and replace this 1 here with that. And we get the square root of -1 times -1 is equal to 1. Now, if you think back to your algebra class, we have the square root of a times b. That's the same as the square root of a times the square root of b. So, I'm just going to apply that rule here. So, square root of -1 times -1 becomes square root of -1 times the square root of -1. And that's equal to 1. But if you think back to my video on all the kinds of numbers, I defined I to be the square root of -1. So we get I times I is equal to 1. And I times I is -1. So now that we have that -1 is equal to 1, if I add 1 to both sides, we get 0 is equal to 2. Now, it's also an obvious fact that 0 is equal to 0. So, if I have two equations, I can average each side, and those averages should be the same. So, I'm going to just take the two equations, 0, I'm going to add the two equations together, and then divide both sides by 2. So 0 plus 0 over 2 is equal to 2 plus 0 over 2. I'm averaging this side, add the two things together, divide by the number of things you're adding together. Same with this side. I'm adding two zeros together, dividing by 2. The average of two zeros is just 0. And this right-hand side, well, 2 plus 0 is 2. Divide that by 2, we get 1. So, we have 0 equals 2, and we have 0 equals 1. And if two things are equal to the same thing, those two things themselves must be the same. So, I'm going to replace this 0 here with the 1 that is also equal to 0 here. So we get 1 is equal to 2. Does that make sense? I mean, we followed all the rules of algebra, right? You should be feeling very weird right now. This cannot be a true fact. It is not possible for 2 to be 1, or 0 to be the same as 1, or 2 to equal 0, or 1 to equal -1. What I'm demonstrating here is that algebraic operations can be very useful in places. And in fact, there are a lot of things you can't do without algebra and manipulations. But if you're not careful, your algebraic manipulations can get away from you, leading you to some incorrect results. How many of you believe me about the first thing that I proved? Let's go back up here and look at it again. How many of you believe that what I've shown here is a correct proof? Is there anything here that any of you can identify that is questionable or is flat out wrong? You can't do that in algebra. Pause, leave a comment if you can find the step that I made a mistake, if I made a mistake. I'm also going to show you a second way of proving this statement. Let's go back down here. We all agree that 1/3 is 0.333 repeating, right? Let's look at this in a couple of different ways. What happens if I take 1/3 plus 1/3 plus 1/3? Okay. If I look at it as purely adding fractions together, well, 1/3 plus 1/3 plus 1/3, well, that's 3/3. But that's 1. Now, let's look at the same thing, but in decimal form. This is perfectly valid. I'm just converting between fractions and decimals. And everybody should agree that 1/3 is 0 point and then an infinite number of 3's that repeat. Let's look at this digit by digit. If I just had 3 of these, I would get 0.9. Okay. If I had 3 of these, I would have 0.99. Okay, what about these? Well, we should end up with 0.999. Going on however far we go, we never end up with a digit that's not 9. So, this sum of 3 of this thing, this is equal to 0.999. It has no other choice. I never get a carry factor from any specific digit. So, I represented the sum of 3 thirds as 1. But in another branch, I represented the same sum in decimal form as this. So they have to be the same. There's also another way to prove this statement using a converging geometric series, but that's beyond the scope of this video. So if you want to make a video about that specifically, I can, if there's enough interest. What is going on here? This is a true statement. And something to give confidence to that is every step I did was completely valid. And I was able to, the important part is I was able to show this fact 2 different ways, both of which are completely valid. It may take some convincing to get you to accept that they're completely valid, but I have confidence I'd ultimately be able to convince you. what happened before. So let's look at these two methods of proving that 2 equals 1 and see what went wrong. Now that you've had some time to think about it and get really uncomfortable with this. Let's go through method 1 step by step and see where we can find a mistake. And this is part of what it is to do math. If you get something that is obvious nonsense at the end of a long proof or some kind of derivation, you go through every step of what you did and think about if that step, something could possibly have gone wrong. So, what did we do in our first step? Well, we just multiplied by a number. There's nothing preventing us from multiplying by a number. Actually, let me do that in blue. That way it's a different color than we've already used. Okay, let's go to our next step. I added a squared. Now, I can add numbers all day long as long as I do it to both sides of the equation. I can do that no problem. Same with subtraction. 2ab is a number that I can subtract. No problem there. This whole thing, that was just a tiny bit of simplification. I can do that because I just factored. And I can factor out a common factor of 2, which leaves this step. Something went wrong here. Why did my division go wrong? Let's look at it. What is a squared minus ab? So we get a hint from this step here. If I look at this step a little closelier, we get a squared equals ab, and then if I subtract ab from both sides, we get a squared minus ab is equal to 0. So when I divided by 0, which you can't do. That is what I did wrong. Because if we were to rewrite this equation faithfully, we would write it as 2 times 0 equals 1 times 0, which is completely valid. Both sides of this equation are just 0. And I could tweak this and have any number over here if I just did the right manipulations. And everything up to that point would still be valid. It's once I do that division that everything breaks. That was not a valid proof because there was an error in it. Now, let's look at the second one. This one is much more subtle. And you may not be able to see it immediately. I know my first time seeing this, I didn't see what went wrong either. It absolutely is true that the square root of 1 is equal to 1. 1 times 1 equals 1. So the square root of 1 equals 1. Okay. And this is absolutely true. Negative 1 times negative 1 is a positive 1. No doubts. Okay, how about this step? Well, I times I is negative 1. That's how I is defined. I is the number whose square is negative 1. Okay, so that leaves this step and this step. So let's look at these steps carefully. This step is completely legitimate. I can do that. the square root of 1 is equal to the square root of -1 times -1. I can write 1 as that product. No problems. It's when I apply this rule. Now, if I say have square root of 36, well, that's the square root of 4 times 9. And yes, I can write that as square root of 4 times square root of 9. Square root of 4 is 2, square root of 9 is 3, which gives us 6. And that is indeed the correct square root of 36. So it's not that the rule itself is wrong, it's that we applied it when we couldn't have. So this rule, the thing that's never really explained very well, is this only works for positive numbers. And the reason for that is exactly as we demonstrated here. If we were to do that with negative numbers, then we end up getting imaginaries out, and they give us negative values where we don't expect them to come up. One of the takeaways that I want to give you guys is that algebra is extremely useful, extremely helpful. We rely on it so much in everyday life. But just brute symbol manipulation without understanding what it is you're doing, it's going to go wrong, and you're going to have to try to figure out where it went wrong. And there's nothing wrong with that. Everybody makes some mistake that they didn't expect. We all do it. I've done it. I still make mistakes like this every once in a while. But you have to know kind of where to look in the case that something does go horribly, horribly wrong. So, does that mean algebra itself is terrible if it's so easy to make these kinds of mistakes? Absolutely not. In fact, I think the biggest problem with it is how it's taught, as just brute symbol manipulation, instead of understanding the things that you're actually working with, these numbers. So why don't you all think about that and take a look at these two proofs of 1 equals this infinite repeating sequence of 9s. If you think you can find an error in either one, please let me know. We can discuss it. Make sure I'm not pulling a fast one on you. So with these, do you expect that there's something wrong with the algebra? If you can't find anything wrong with the algebra, then why does it bother you so much? Is it because of how 1 and this infinite sequence of 9s look completely different and completely unrelated? Well, maybe it's not the algebra if you can't find a mistake and can't find a reason why it shouldn't be true. Maybe it's our understanding of what numbers really are and what these representations that we write down for convenience sake actually mean. Because in a similar vein to this, I can also show that another way to write 0.5 is 0.4 with an infinite sequence of 9s after it. Or 0.25 is 0.24 with an infinite sequence of 9s after it. They're both perfectly valid. And so we have this non-uniqueness of decimal representations because of these fringe cases. That doesn't mean that something has gone horribly wrong. It just means that our intuitions are not the most reliable. indicators of whether we've done math correctly or not.